Hey guys, we're going to start 3.5 now. So go ahead and try your warm-up. The warm-up's really important today because we are going to be curve sketching. So being able to identify and graph our asymptotes correctly is going to come in super handy. All right, so let's look at this. This is a great review of all the different ways that we have asymptotes and how to find them. So number one is vertical asymptotes. Remember, to find your vertical asymptotes, you're going to set the denominator equal to 0. So this one we would have x squared minus 5x plus 6 equals 0. We'll factor that. So minus 2 minus 3. And so I'm going to have my vertical asymptotes at x equals 2 and x equals 3. All right, number two, horizontal asymptotes. And remember, with horizontal asymptotes, there's those three situations, and it all has to do with the highest power in the numerator and the highest power in the denominator. So let's look at A. On A, my power in my numerator is higher than my power in my denominator. And when that happens, we have no horizontal asymptotes. Okay, on B, you'll notice that we have the same power in the numerator as in the denominator. So on B, that's the situation where our horizontal asymptote is going to be the coefficients of that highest power. So this one would be y equals 3 over 2. And then on C, we have the denominator with a higher power than the numerator. And in this case, it doesn't matter what the coefficients are, what the powers are. If your bottom power is higher than your top power, you automatically have a horizontal asymptote at y equals 0. All right, feel free to add some extra notes in there that we just talked about for A, B, and C of the rules and like how you know what we got there. Okay, let's go to number 3. This is the last one, the slant asymptote, the oblique asymptote. This happens when your numerator is 1 degree higher than your denominator. Okay, so on this one, you'll see I have a 2 on the top, I have a 1 on the bottom in terms of the highest exponent. So this would be a slant asymptote. And so the way that we find that is we're actually going to do long division using our functions. All right, so first we're trying to see what do we need to times 2x by to make it into x squared. So I need to get rid of the 2. I'm going to times it by a half. I need to add an x to make it x squared. So it's going to be x half x. Okay, so that gives me x squared plus x. And I want to subtract that. When I subtract that, my x squareds go away. I get negative 2x, bring down the plus 4. Okay, to make a 2x into a negative 2x, I want to times it by negative 1. Now I'm going to subtract that. Okay, my 2x's will cancel, and I will get 6. That is my remainder. I actually don't care about my remainder on this because my slant asymptote is just going to be the stuff that I got before the remainder. Okay, and obviously it's in the form of a linear equation because it's a slant asymptote. Okay, it's a line. It's always going to be a line because the top is 1 degree higher than the bottom. So when we divide them, we'll always end up with a single x, a linear equation. All right, so today we are going to talk about concavity, inflection points, and the second derivative test. And then we're going to practice some curve sketching using all of these skills put together with the stuff from 3.1 through 3.4. Okay, so first let's talk about concavity. Concavity means which way the function is curving, okay? So if you have concave up, it looks like that. If you have concave down, it looks like that. And the easiest way to think about it is if you were to drop water, if it was raining on this function, would the function collect the water or would the water roll off? Okay, so if it would be collecting the water, that's concave up. If it would be rolling off, that's concave down. All right, so the concavity theorem says if your second derivative is positive, it is concave up. If it is negative, it is concave down. Okay, so basically we're going to do our second derivative. We're going to look at the values at which we're positive, the values at which we're negative, and that tells us concave up or concave down. All right, the next thing is inflection point. So you have an inflection point when your concavity changes. Okay, so let me just show you an example. If you have something that's concave up and then all of a sudden it becomes concave down, between those two, you have a spot where there's called an inflection point, and that's just where the graph changes from being concave up to concave down, or vice versa, concave down to concave up. The way that we find our inflection point is by setting our second derivative equal to 0. All right, the last thing is our second derivative test, and I think you guys are going to like this because this is going to give us a shortcut to find our extreme values where we don't have to make a number line. So let's look at the second derivative test. Basically, what we're going to do is we're going to find our critical points. So remember, our critical points are our first derivative set equal to 0. Then we're going to plug those points into the second derivative. If the second derivative at that point is negative, then we have a max. If it's positive, then we have a min. Okay, and that should make sense to you because think about it. If you are concave up at that point, that's a minimum. If you are concave down at that point, that's a maximum. So that's where the positive or negative comes in with the second derivative. All right, let's try an example. Number 1, determine where the graph of f of x equals x cubed minus 3x squared plus x minus 2 is concave up or concave down. Okay, so first thing we want to do is find our first and second derivative. So first derivative, 3x squared minus 6x plus 1. Second derivative, 6x minus 6, and I can go ahead and factor out a 6. That's going to be handy. Okay, so concave up, concave down. I want to think to myself, what values of x are going to make this positive? What values of x are going to make this negative, okay? And you should notice here at 1, it's 0. So I know that before 1, it's either going to be positive or negative, and then after 1, it's going to change. Okay, so let's think. If I'm before 1, so let's say I'm at 0. In here I have a negative 1. That gives me a negative 6, okay? So that means I'm negative on the left side of 1. That means I'm going to be concave down in that interval. Okay, if I'm on the other side of 1, let's say I'm at 2. 2 minus 1 is 1. 1 times 6 is 6. That's positive. So I'm going to be concave up on the right side of 1. 1 to infinity. All right, let's look at the next one. Find the inflection points. Okay, well, we basically have that already done because if I'm changing from concave down to concave up, that's where my inflection point is. So at 1 is where I'm changing, and so 1 is my inflection point. Algebraically, all you gotta do is set that second derivative equal to 0. So I have an inflection point at x equals 1. All right, the last part here, find and classify the extreme values of the function. Okay, so extreme values means maxes and mins. This is back from the beginning of unit 3, okay? So the first thing I want to do, take my first derivative, set it equal to 0. Find my critical values. On this one, it actually does not factor, so I'm going to use the quadratic formula. So I have negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, when you go ahead and simplify the radical and simplify down the fractions, you end up with 1 plus or minus square root of 6 over 3. And just for our own knowledge, radical 6 over 3 is like 2.8, and it's irrational, okay, so it goes on from there, but it's somewhere around like 2.8, okay, and that's just going to be important for us. No, not 2.8, 0.8. And that's going to be important for us just in a minute when we think about the, okay. All right, so I want to know, I found my extreme values. Okay, it's going to be 1 plus radical 6 over 3. It's going to be 1 minus radical 6 over 3. Now I want to know if those are going to be maxes or mins. Okay, so it says find and classify. So I have to find if they're maxes or mins. All right, so this is where our second derivative test is going to come in. It's super handy, okay? So let's start with the 1 plus radical 6 over 3. What I want to do is I actually want to plug that into my second derivative, okay? So if I plug that into my second derivative, I get 6 times 1 plus radical 6 over 3 minus 1. Okay, so I'm plugging that into my second derivative. If you forget, that's right here, okay? So in the inside of this parenthesis, the ones are going to cancel. So I'm going to get this 6 times radical 6 over 3. I don't really care what this equals. I just care about it being positive or negative, okay? It is positive. What that means is that at this point, the graph is concave up, which means that this point is a minimum. Because if I'm concave up, that extreme value has to be a min. Okay, so I'm going to write down that this one is a minimum. All right, my other one was x equals 1 minus radical 6 over 3. Okay, so I'm going to plug that in to my second derivative. And for the sake of myself saving a little bit of space here, I'm going to go back up here. It's the same thing, except it's a minus, right? So basically, I get a negative in here. That makes my second derivative negative. That means at this point on the graph is concave down. If I'm concave down, I have a maximum at that point. All right. Okay, we're going to move on. We're going to try some curve sketching. All right, at the top, we have a guide to curve sketching. This is basically like if you don't have a calculator, which on the final you may not, and you need to sketch a curve. These are the ways that you get a really nice curve. And remember, it's a sketch, okay? So we're not going to have a table of values and have a bunch of really exact points, but we are going to be pretty close, okay? So let's look this over. Number one, we want to think about our domain and range. That comes a lot into play if you have like a radical or something like that. Okay, number two, we want to find our x and y intercepts. Remember how to do that. That's where for our x-intercepts, we're going to set y equal to 0. For our y-intercepts, we're going to set x equal to 0. Okay, we want to think about symmetry. So for instance, like a parabola has symmetry. Number 4, we want to find all of our asymptotes, vertical, horizontal, and oblique. Number 5, we want to think about where the function is increasing and decreasing and the relative extrema. So those are both first derivative things. We're going to use the first derivative for that. And then we also want to think about concavity and inflection points, and those are second derivative things. All right, so let's go through a couple examples here and show you how to do these. Okay, so this should actually be example 2 and example 3. I have them misnumbered. All right, so let's look at example 2. We're going to sketch this curve. So we're going to just kind of go through the things here. So let's first think domain and range. This one, there is no problems with any x values that I would ever want to plug in here. Okay, so for domain and range, I'm not really going to worry about it. Let's do our x and our y intercepts. Okay, so we'll start with our x intercepts. So for my x intercepts, I want to set my y equal to 0. And I want to solve this out. Okay, so I'm going to factor out an x squared. And I see that I have an x-intercept at 0 and also at 3. All right, next I want to find my y-intercepts. So that is where I put my x equal to 0. So my y-intercepts are just at 0. Y-intercept. Okay, the next thing is asymptotes. I do not have any asymptotes because I do not have a rational function, meaning a fraction. Okay, so I'm going to skip that. And now we're going to go to increasing, decreasing, and extrema. Okay, so remember, that's my first derivative stuff. So let me take my first derivative. I get 3x squared minus 6x, and I want to set that equal to 0. I'm going to actually factor out a 3x here. And it looks like I'm going to get x is equal to 0 and x is equal to 2. All right. Okay, now I'm going to go ahead and do my second derivative. I'm going to go over here for that. So I'm doing the derivative of the first derivative now, okay? So it's going to give me 6x minus 6. I want to set that equal to 0. I'm going to factor out a 6. And I get x equals 1. All right, so let's go back to our first derivative. We have critical points at 0 and 2. That means they might be a max, they might be a min. We're actually going to use our second derivative test now to see whether they are maxes or mins. Okay, so what we're going to do is we're going to plug in the 0 and the 2 into our second derivative. Okay, so let's start with the 0. 6 times 0 minus 6, that gives me negative 6. Since it is a negative, it means it is concave down, and it means that at 0 I have a maximum value. All right, let's try the 2 now. 6 times 2 minus 6, that gives me 6. That is a positive. It means at that point it is concave up, which means at 2 I have a minimum value. Okay, now this actually tells me increasing or decreasing as well. Okay, so let me just draw a quick number line. I have 0, I have 2, I have a max at 0, I have a min at 2. If you have a maximum at 0, it means up until that point it was increasing. After that point it was decreasing. Then I have a minimum at 2. So I was decreasing down to 2. Now I need to increase again. Okay, so I hope that makes sense to you. I'm doing hand motions that you can't see. But basically, if you're going up to a max, you have to be increasing up until that point. then you have to start going down, okay? All right, let's go over here to the second derivative, x equals 1. That is an inflection point. So remember, our second derivative, if we find it equal to 0, that's an inflection point, okay? So what that means is, at that point, the graph is changing from concave up to concave down, or from concave down to concave up. It's changing at that point, okay? So let's just make a quick number line. Here's my point 1. If I am below 1, say at 0, well, I already plugged in 0 over here, right? I got -6. Since it's negative, that's concave down. So I actually already did this part when I was doing my max and my min. Over here, if I were to plug in, say, 2, remember I got 6. That was a positive. That means over here it's concave up. All right, we're going to go ahead and sketch our graph now with all of this information. The last thing that I need actually before I sketch my graph, and I'm going to start it and then I'll show you. So let's start with our x and our y-intercepts. X-intercepts at 0 and 3, 0 and 3. Y-intercept at 0, already have it. All right, next I have my max and my min. My max is at 0, I already have that point on the graph, 0, 0. My min is at 2, I want the y value. So let me do that. So here I have the point 2. I want to plug in the 2 into my equation to find the f of x, the y coordinate, and it's -4. So get your point at 2, -4. All right, I have an inflection point at 1. Okay, if I plug in the point 1 into my f of x, I get -2. So I'm going to put that on the graph. And then I know I'm increasing to 0. Then I'm going to decrease. And then I'm going to increase. Okay. And there's my sketch. All right, you can pause it if you need more time, but I'm going to erase it so that I can do number 2. All right, so let's look at this last one here. Let's go through the steps. Okay, so domain and range. Doesn't seem like we have any limit on our x values. Okay, so number 2, x and y intercepts. Okay, so let's do that first. So we're going to, first we'll find our x intercepts. So that would be where I set my y equal to 0. Okay, since I have a fraction, my denominator actually does nothing to help me equal to 0, so I'm just going to set the numerator equal to 0. Okay, so I know I'm going to have a x-intercept at 0. Let's do our y-intercepts. So our y-intercept is where we actually make x equal to 0. And that's just going to be 0 as well. So I'm just going to have 1 point, 1 intercept at 0, 0. All right, let's go to the next thing, asymptotes. Okay, so first let's think about vertical asymptotes. So remember, vertical asymptotes are where my denominator is equal to 0. Since it's x squared plus 1, there's no vertical asymptote. Okay, so no vertical asymptotes. Horizontal, this is where we're looking at the highest power in the numerator and the denominator. Looks like my denominator is higher than my numerator, which means I will have a horizontal asymptote at y equals 0. Okay, I'm going to write down no vertical asymptotes. Okay, next we want to do our first derivative because that's going to tell us our critical points, our extrema, our increasing and our decreasing. Okay, so I'm going to do my first derivative. So I have quotient rule, all right? Here we have derivative of the top times the bottom minus derivative of the bottom times the top. over the bottom squared. Okay, I want to set this equal to 0. Remember, the denominator does not help me equal 0. I don't want to even really worry about it, okay? I just want to worry about my numerator. So I have 4x squared plus 4 minus 8x squared. So that's negative 4x squared plus 4. I can factor out a negative 4. Okay, and so if I set this equal to 0, I get x is equal to positive or negative 1. Okay, remember with your maxes and mins, you actually want that point, the full point with the x and y value. So my first point, 1, if I plug it into the equation, I get 2. And then my second point, negative 1, plugging it in, I get negative 2. All right, let's move on to our second derivative. Okay, so this is going to be quotient rule again. Okay, and so I'm going to use, let me erase. All right, so I'm actually going to use, for my first derivative, remember how we had simplified the numerator? It was negative 4x squared plus 4 over my denominator, x squared plus 1 squared. Okay, so this is my first derivative that I want to take the derivative of for my second derivative, and this is also quotient rule. I'm coming up here. All right, so we have derivative of the top, negative 8x times the bottom, x squared plus 1 squared, minus derivative of the bottom. This is chain rule, so 2x squared plus 1 times 2x times the top. All over the bottom squared, so our squared becomes a 4. All right, I'm setting this equal to 0. And let's see. I think what I want to do first is, do you notice that I have an x squared plus 1? I have 1 here. This will become a 3. This will become a 1. Okay. Now, since I'm setting this equal to 0, I do not care about my denominator, so I'm just going to set my numerator equal to 0. But I was happy to cancel some things before I got rid of my denominator because it's just going to make it easier. All right, so I have my numerator, 0 equals, I'm going to distribute the negative 8x right now. So negative 8x cubed minus 8x. Okay, over here, what if I took this negative 2 and this 2x? So that's a negative 4x, okay? And now I'm going to distribute that into this parenthesis. Okay, this is gone. All right, so that's going to give me plus 16x cubed minus 16x. All right, now I'll combine some like terms. So I have 8x cubed minus 24x. I'll pull out an 8x, x squared minus 3. Okay, so I have two values here, and those would be x equals 0 for the 8x. The other one is positive or negative radical 3. Okay. Okay, so now I'm going to make a number line. I'm just trying to figure out the best place to do this. And so I have my 0, my negative radical 3, my positive radical 3. And so I want to put some values in to my second derivative. Remember, for the second derivative, you want to use this, but you want to have that denominator on the bottom. Actually, you know what? Since the denominator has a squared, it's always going to be positive. So really, we can just use this, I think. All right, so we're going to try testing out some values here. The square root of 3 is like 1 point something. So if I use -2 for a test value, and then I could use 2, I could use 1, I could use -1. Those are fine values to test. All right, so if I plug in my -2, I'm going to get a negative. So at this point, we are concave down. Concave down. -1 is going to give me a positive, so that is concave up. Here, 1 gives me a negative, so concave down. And then at 2, I get a positive, concave up. That means these are going to be inflection points. All right, let's go back to our 2 extreme values, 1, 2, and -1, -2. And so at 1, 2, remember at 1 up here, it was concave down. So that means this is going to be a max. Okay, at -1, I was concave up, so that means this is going to be a min. All right, so now I'm going to get my graph. Oh, Lord. Okay. All right, first thing I want to put on here is my intercept at 0. I have a max at 1, 2. I have a min at -1, -2. And I have an asymptote at y = 0. That's going to be important. So remember, when you have a horizontal asymptote, it doesn't mean you can't cross it. It means that as we go out to the left and to the right, our graph is going to hug that line, okay? All right, so let's start drawing our graph. Remember, you have a min here. That means I want to start above it. I want to go down to it, and then I'm going to go up. Okay, so minimum value here, and then I went up from there, maximum value at 1, 2. And you can see the inflection points would be like here, where my inflection changed. I had 3 of them. You don't need your inflection points. I'm just showing you where the graph kind of changes concavity. All right, you are trying 3 graphs, okay? So use the techniques that we were just doing. And, you know, some of those second derivatives, like on C, gets a little bit messy. Just do your best. Remember that your denominator doesn't help you equal 0, so you can, once you cancel anything that you can cancel, just go ahead and look at the top. All right, I'll talk to you guys soon.